useful formula coming out of it, and that's what perturbation theory is about, and we'll actually do it. We'll find, for example, we will find this term here, E1, the so-called first order correction to the eigenenergies. We'll find a formula for this that's quite simple and very easy to work with, assuming that your eigenfunctions for the unperturbed problem system have exact solutions. Then finding a term for this, the first order correction to that energy, the eigenvalues, is easily calculated, as you'll see soon. Okay, probably next square in this session. All right. Now the ends here, little ends here, well, they're just the different eigenstates. Right? You're used to that. So here's our eigenequation, just Schrödinger equation for the energy. Right? As I was saying, the coefficients of the lambdas. So this will become a power. The left-hand side will be a power, an expansion in powers of lambda, and each of those, the coefficients of each power of lambda has to be 0. So, okay. For example, the 0th power, when you look at the coefficient of the 0th power of lambda, so lambda to power 0, which is 1. Okay. Do this for homework. You'll find that you get this. So in other words, you get h0 hat un0 minus en0 un0 equals 0. Right? So you end up getting the original eigenequation for the unperturbed system that you're talking about. Okay. Now for the first order lambda, so you plug in this and the modified Hamiltonian into this general eigenequation. You get the expansion in terms of powers of lambda. Okay. And then you look at the coefficient of the power of lambda to first power, so just lambda to the 1, right? And that coefficient that you let be 0, because all the coefficients have to be 0 because of this, you will get this, right? Now I've labelled it star circle or asterisk circle, because I'll be referring back to this in next square, next half session. So do it for homework. Homework. It's not difficult. A little bit of algebra. Okay. Now the 1 here, for example, comes from the fact from here, because it's just the first power. Okay. And the h dashed comes from the general h, the perturbed h, and so on. Okay. So. This first order correction, this eigenequation, if you like. Can you call it an eigenequation? No, you can't. Okay, this equation, a little bit more complicated than this one. Now this is an eigenequation because you've got eigenfunctions here and eigenvalue. Now we can use this in later theory. So I've ID'd it. I've started. Okay, and I'll turn around. Now, so we now use this equation, and we'll start operating on this. Now, what do we know? We don't know that yet. We know these, right? This we don't know yet. This we know. This we know. So what do we don't know? The first order energy eigenvalue. So we don't know that, right? We're trying to calculate that, and we don't know this either. This is the first order correction to the eigenfunctions here. We don't know that. We don't know that, and we don't know that. But we do have this relationship here, right, that we found by equating the coefficient of lambda to first power in this equation, this general eigenequation, and we got this, right? Now, let's see, what are we going to do now? So, the UN1 and En1 here, they're our two unknowns. So we'll start playing with this equation, this star circle equation, and see if we can find formula for the UN1, the first order correction of the eigen functions, and En1, first order correction to the eigen energies, the eigenvalues. Alright, well, the U naughts here, they are, from earlier theory, what was it, chapter, I don't remember, I haven't written it up. Anyway, these eigenfunctions here, they form, if you remember from earlier theory, earlier chapter, they form a complete orthonormal set, right? So we can write any function, we can expand any function in terms of that complete orthonormal set. Right? So let's do that. So we're trying now to find an expression for the UN1, the first order correction to the eigenfunctions here, and we're just going to expand that out in terms of these bases. There are bases, right? These functions here. We did that from earlier theory. Okay. So these are just the coefficients, and so you have a weighted sum of basis functions giving you any term you like. Okay. So so we now have the first order correction of the eigenfunctions UN1 in terms of some constants, or series of constants, in terms of the eigenfunctions 0. Now we know these, right? We know these. They are from your basic problem, the system that you started with, that you assume has exact solutions. Right? So these terms here will be in relatively simple form. There won't be numerical approximations or untidy stuff like that. They'll be in some clean mathematical form, right? Okay, now, alright, so we've assumed that the first order corrections to the eigenfunctions are of this form. This is known. Now we're trying to find what these coefficients are. Well, we have this relation, and we have this equation from earlier. Now here's the UN1 term here, and we've got an expression here for UN1. So plug in this here, right? And again, it's not difficult. So I ask you to do it for homework. I don't know if you've been noticing, but as we get further and further into the text, often, well, increasingly, the mathematical results are getting harder, and in a sense, because there's an introductory text to quantum mechanics, assume it's the first quantum mechanics course that you've done. So in a sense, Davies has been flying, what I call flying over the icebergs a bit. So just you only see the upper 10%. You know an iceberg, 9/10 of it is underwater, right? Given the relative density of ice compared to water. Ice, when it becomes ice, when the water freezes, it expands actually, so it becomes less dense, and hence it floats, right? But it's only a little less dense than water, so most of the ice is under the water, like 9/10 of it. So, by analogy, as it's getting harder, and he's just Davies and Betts introducing you to concepts in quantum mechanics, and often they gloss over details. Like there's one coming up which I didn't follow too well. I'd need to, I'm not a particular expert in perturbation theory, but I'd probably need to go to master's level texts to understand the details of what they're talking about. So sort of expect that, because it's been happening a bit lately. But this part of perturbation theory is relatively easy.